Welcome to our deep dive into sequential logic design, a foundational concept in digital electronics. Unlike combinational logic where outputs depend solely on current inputs, sequential logic introduces memory into the system. This means outputs are determined by both present inputs and past states. In this video, we'll explore the building blocks of sequential circuits, including flip-flops, counters, and registers. We'll also discuss how these elements work together to create complex digital systems. Whether you're a student or a professional, understanding sequential logic is essential for designing reliable and efficient digital devices. Let's start by exploring the basic components that make sequential logic possible. At the heart of sequential logic circuits are flip-flops. These are bistable devices, meaning they have two stable states and can store a single bit of information. Flip-flops are essential for memory elements in digital systems. They can be triggered by input signals and are used to build more complex circuits like registers and counters. There are several types of flip-flops, each with unique characteristics and application. In the next few scenes, we'll break down the most common types and see how they function within a circuit. SR or set reset flip-flop is one of the simplest types. It has two inputs, set S and reset. When the set input is activated, the output switches to one state, and when the reset is activated, it switches to the other. If both inputs are inactive, the flip-flop maintains its previous state. However, if both are active simultaneously, the output becomes unpredictable, which is generally avoided in practical design. SR flip-flops are often used in simple memory storage applications and as building blocks for more complex flip-flops. JK flip-flop addresses the ambiguity found in the SR flip-flop when both inputs are active. It has two inputs, labeled J and K. When both are high, the output toggles its state. If only J is high, the flip-flop sets. If only K is high, it resets. This versatility makes the JK flip-flop a popular choice in counters and other sequential circuits. Its ability to toggle is particularly useful in designing frequency dividers and binary counters, making it a staple in digital design. D or data flip-flop is designed to eliminate the uncertainty of the SR flip-flop. It has a single data input and a clock input. On the triggering edge of the clock, the output takes the value of the data input. This makes the D flip-flop ideal for data storage and transfer applications such as registers. Its predictable behavior ensures that data is reliably captured on each clock cycle, making it a fundamental component in synchronous circuits. T or toggle flip-flop is a simplified version of the JK flip-flop. It has a single input, and each time it receives a clock pulse, it toggles its output state. This makes it extremely useful in designing binary counters, where each flip-flop represents a binary digit. The T flip-flop simplicity and toggling action are key in frequency division and counting applications, making it a go-to choice for designers working with sequential logic. The flops can be triggered in two main ways: level-triggered and edge-triggered. Level-triggered flip-flops respond to the input signal as long as the clock is at a certain level, either high or low. Edge-triggered flip-flops, on the other hand, only respond at the moment the clock signal transitions, either from low to high rising edge or high to low falling edge. Edge-triggered designs are preferred in synchronous systems because they reduce the risk of glitches and ensure precise timing. Further improve reliability, master-slave flip-flops were developed. These consist of two flip-flops connected in series. The first, called the master, captures the input on one phase of the clock, while the second, the slave, updates the output on the opposite phase. This arrangement prevents unwanted changes during the clock transition and ensures that outputs only change at specific times. Master-slave flip-flops are widely used in synchronous circuits to maintain data integrity. Analyzing sequential circuits involves understanding how the circuit transitions from one state to another based on inputs and current states. This process typically starts by identifying the type and arrangement of flip-flops used. Next, you examine how inputs affect the state transitions. By systematically analyzing the circuit, you can predict its behavior and ensure it meets the desired specifications. This analysis is crucial for troubleshooting and optimizing digital design. State tables are a powerful tool for representing the behavior of sequential circuits. They list all possible states of the circuit, the inputs, and the resulting next states and outputs. By organizing this information in a table, designers can easily visualize how the circuit responds to different input combinations. State tables are especially useful for complex circuits with multiple flip-flops and inputs, providing a clear roadmap for analysis and design. State diagrams offer a graphical way to represent the operation of sequential circuits. Each state is depicted as a circle, with arrows showing transitions between states based on input conditions. State diagrams make it easier to visualize the flow of the circuit and identify potential issues, such as unreachable states or unwanted loops. They are often used alongside state tables to provide a complete picture of circuit behavior. Synchronous sequential circuits are those in which changes in state occur only at specific times, determined by a clock signal. This synchronization ensures that all parts of the circuit update together, reducing the risk of timing errors. Synchronous circuits are the backbone of modern digital systems, from microprocessors to memory devices. Their predictable behavior makes them easier to design, analyze, and troubleshoot. Designing a synchronous sequential circuit begins with defining the desired behavior, often using state tables or diagrams. Next, you choose the appropriate flip-flops and determine how to connect them to achieve the required state transitions. Logic gates are then added to control the inputs to each flip-flop based on the current state and external inputs. Finally, the design is tested and refined to ensure it operates as intended. Counters are a special type of sequential circuit used to count events, clock pulses, or other occurrences. They are widely used in digital clocks, timers, and frequency dividers. Counters can be designed to count up, count down, or both, and can be implemented using various types of flip-flops. In the next scenes, we'll explore the two main types, asynchronous and synchronous counters. Synchronous counters, also known as ripple counters, are built by connecting flip-flops in series. The output of one flip-flop serves as the clock input for the next. This design is simple but can lead to timing issues as changes ripple through the flip-flops one by one. Asynchronous counters are suitable for low-speed applications where precise timing is not critical. Synchronous counters solve the timing issues of asynchronous designs by connecting all flip-flops to the same clock signal. This ensures that all flip-flops update simultaneously, providing accurate and reliable counting. Synchronous counters are preferred in high-speed applications and are commonly found in digital systems that require precise timing, such as processors and communication devices. Counters are used in a wide range of applications, from simple event counting to complex digital systems. They can be found in digital clocks, frequency dividers, and even in microprocessors for instruction sequencing. Counters can be designed to reset at a certain value, count in binary or decimal, and even generate specific timing signals for other parts of a circuit. Shift registers are another important sequential circuit. They consist of a series of flip-flops connected so that data can be shifted in or out, one bit at a time with each clock pulse. Shift registers are used for data storage, transfer, and manipulation. They can move data left or right, making them useful for serial to parallel and parallel to serial conversion. There are several types of shift registers, including serial in serial out, serial in parallel out, parallel in serial out, and parallel in parallel out. Each type serves a different purpose, depending on how data needs to be moved or stored. For example, serial in parallel out registers are used to convert serial data streams into parallel data for processing. Universal shift register combines the features of all basic shift registers. It can shift data left or right, load data in parallel, and output data in either serial or parallel form. This versatility makes universal shift registers valuable in complex digital systems where flexible data handling is required. Registers are used extensively in digital systems for temporary data storage, data transfer, and manipulation. In microprocessors, registers hold data that is being processed or transferred between different parts of the system. Shift registers, in particular, are used in communication systems, data conversion, and signal processing. Timing diagrams are essential tools for understanding how sequential circuits operate over time. They show the relationship between clock signals, inputs, and outputs, making it easier to visualize how data moves through the circuit. Timing diagrams help designers identify potential issues, such as setup and hold time violations, and ensure that circuits function as intended. Read a timing diagram. Start by identifying the clock signal, which serves as the reference for all other signals. Next, observe how the inputs change in relation to the clock and how the outputs respond. Pay attention to the timing of data capture and output changes, as these are critical for reliable circuit operation. Practice with timing diagrams is key to mastering sequential logic design. Setup and hold times are critical parameters in sequential circuits. The setup time is the minimum period before the clock edge during which the input must be stable. The hold time is the minimum period after the clock edge during which the input must remain stable. Violating these requirements can lead to unpredictable circuit behavior, so designers must ensure that all signals meet these timing constraints. Let's walk through the design of a simple 3-bit synchronous counter. We start by defining the states, which range from 0 to 111. Next, we create a state table showing how the counter transitions from one state to the next with each clock pulse. Using JK flip-flops, we determine the required logic for each flip-flop input. Finally, we draw the circuit diagram and verify its operation using a timing diagram. Assigning binary codes to states is an important step in sequential circuit design. The choice of state assignment can affect the complexity of the resulting logic. Common strategies include binary, gray code, and one-hot encoding. Each has its advantages depending on the application and design constraints. Once the state table and assignments are complete, the next step is to minimize the logic required to implement the circuit. Techniques like Carnot maps and Boolean algebra are used to simplify the logic expressions for each flip-flop input. This reduces the number of gates needed, saving space and power in the final design. With the minimized logic expressions, you can now build the circuit using flip-flops and logic gates. Careful layout and wiring are essential to avoid timing issues and ensure reliable operation. Simulation tools can help verify the design before physical implementation, catching potential errors early in the process. Testing is a crucial part of sequential circuit design. By applying different input sequences and observing the outputs, you can verify that the circuit behaves as expected. Debugging tools such as logic analyzers and simulation software are invaluable for identifying and fixing issues. Thorough testing ensures that the final circuit is robust and reliable. Even experienced designers can run into pitfalls when working with sequential circuits. Common issues include race conditions, glitches, and timing violations. Careful analysis, proper synchronization, and thorough testing are key to avoiding these problems. Always double-check your design for potential hazards before moving to production. As your designs grow in complexity, you may need to expand your circuits to handle more states or data. This often involves adding more flip-flops, counters, or registers. Modular design techniques can help manage complexity, making it easier to test and maintain large systems. Always plan for scalability in your initial design. Choosing between synchronous and asynchronous design depends on your application's requirements. Synchronous circuits offer predictability and ease of analysis, while asynchronous circuits can be faster and use fewer resources. However, asynchronous designs are more prone to timing issues and are generally harder to debug. Most modern systems favor synchronous design for its reliability. Sequential logic circuits are everywhere in modern technology, from simple timers and counters in household appliances to complex processors in computers and smartphones. These circuits form the backbone of digital electronics. Understanding how to design and analyze them opens the door to a wide range of engineering opportunities. Central processing units, CPUs, rely heavily on sequential logic. Registers store data, counters keep track of instructions, and state machines control the flow of operations. Mastering sequential logic design is essential for anyone interested in computer architecture or embedded systems. Memory devices, such as RAM and ROM, use sequential logic to store and retrieve data. Flip-flops form the basic storage elements, while registers and counters manage data flow. Efficient memory design depends on a solid understanding of sequential circuits and their timing requirements. In communication systems, sequential logic is used for encoding, decoding, and error checking. Shift registers handle data serialization and deserialization, while counters and state machines manage protocols. Reliable communication depends on precise timing and robust sequential circuit design. Signal processing often involves sequential circuits for tasks like filtering, modulation, and data conversion. Registers and counters are used to manage data streams, while state machines control processing steps. Mastery of sequential logic is key to designing efficient signal processing hardware. Sequential logic circuits are widely used in industrial automation for controlling machinery, monitoring processes, and ensuring safety. Programmable logic controllers, PLCs, rely on sequential circuits to execute control sequences and respond to sensor inputs. Robust design is essential for reliable operation in demanding environments. When issues arise in sequential circuits, systematic troubleshooting is essential. Start by checking power and clock signals, then verify flip-flop operation and logic connections. Use timing diagrams and simulation tools to pinpoint problems. Patience and attention to detail are key to resolving complex issues. Modern simulation tools make it easier to design, test, and debug sequential circuits. These tools allow you to model circuit behavior, visualize timing diagrams, and catch errors before building physical prototypes. Investing time in learning simulation software pays off with faster, more reliable designs. Once your design is complete and thoroughly tested, it's time to move to implementation. This may involve programming a field programmable gate array (FPGA) or designing an application-specific integrated circuit (ASIC). Careful planning and documentation ensure a smooth transition from design to hardware. Sequential logic continues to evolve with advances in technology. New materials, faster transistors, and improved design tools are enabling more complex and efficient circuits. Staying up to date with the latest trends ensures your skills remain relevant in a rapidly changing field. There are many resources available for learning more about sequential logic design. Textbooks, online courses, and simulation software provide valuable information and hands-on experience. Joining online communities and forums can also help you connect with other designers and stay informed about best practices. In this video, we explored the fundamentals of sequential logic design, including flip-flops, counters, registers, and timing diagrams. We discussed how to analyze and design sequential circuits, avoid common pitfalls, and apply these concepts in real-world applications. Mastery of sequential logic is essential for anyone working in digital electronics. Thank you for joining us on this journey through sequential logic design. With a solid understanding of flip-flops, counters, registers, and timing diagrams, you're well equipped to tackle more advanced topics in digital electronics. Continue practicing, exploring new designs, and expanding your knowledge to become a proficient digital designer.